Okay. So, with that kind of prelude, let us get into the definition of vectors and vector spaces. Okay. As I had said last week, vector is basically an ordered set of real numbers. Vector is an object that has a magnitude and a direction, and we represent vectors as a point in the Euclidean space. So, let us say this particular point is 1 comma 2. We often denote it in this manner to really indicate that the vector has a size and a direction. Okay. A vector space is nothing but a collection of Euclidean vectors along with the rules of addition and scalar multiplication. Now, what are those rules of addition and scalar multiplication? So, if you have a scalar alpha and a vector x bar, then alpha x bar also exists and also lies in the same vector space. You have the vector space is defined as a space that also has a vector 0 bar. 0 bar means 0 0 or 0 0 0 or whatever the case might be. All the elements of that particular vector, when those are 0, then that vector is 0 bar. The other requirement is that if vector x bar exists, then a vector negative x bar also exists, such that x bar plus negative x bar equals 0 bar, right. You have the thing of multiplication of scalars, scalar with summation, that is alpha x bar plus alpha y bar. If x bar and y bar are vectors in a particular vector space, then alpha times x bar plus y bar also is in that same vector space. Okay. And because y bar can be negative x bar, 0 bar also has to be in that vector space. So, let us take an example. Let us say we say that we claim that first quadrant, for example this, we claim that this is a vector space. Is this possible to be a vector space? No, it is not a vector space because the vector minus x bar does not exist in that space. Okay. So, any partial part of this particular space will not be a vector space because there would be a vector that is present in that space which would not be represented as okay. On the other hand, let us say we had this particular line which passes through the origin. That line is a vector space. Why? Because all of these rules that we talked about will still be valid. This particular vector, let us call that as z bar, that vector is immaterial to that particular vector space. Why? Because z bar does not exist in that vector space. Okay. So, let us say you have a plane over here. Okay. A vector like this is not a part of that vector space. So, therefore, all of the definitions that we talked about are not really applicable to that vector, that particular vector. But if we were to talk about this quadrant, this vector is in that vector space, okay, but minus of that is not in that vector space. So, therefore, quadrant 1 cannot be a vector space. Okay. So, for some of you this might be a little bit confusing, at least for me it was, because I had learnt all these linear algebra. I have gone through two courses of linear algebra without really formally defining a vector space, and then the question was, why is so much, why do we make so much out of the vector space and so on. The reason is basically all the examples that you have dealt with in the past in your linear algebra courses, by definition you were working with the vector spaces. You never came across an example of something that was not in a vector space. So, this question never occurred to you, okay. But once we formally define, yes, then we have to be careful about what is a vector space or what does not constitute a vector space, okay. So, all those rules of addition, scalar multiplication and all that you have learnt, they are all valid. 0 multiplied by x bar is 0 bar, that is valid. x bar plus negative x bar equal to 0 bar, that is valid. X bar plus y bar equals y bar plus x bar, that is also valid. A vector space, a space where that is violated will not be a linear, will not be a vector space, because that will not be a linear space. Okay. The other confusion that I have seen some of the students have is about linearity. Again, why are we making such a big deal about vector space and that the vector space is a linear space? Okay. So, if you want to consider this function f of x equal to c1 x1 plus c2 x2, where x bar is x1 x2, right. We know that, we kind of know that this is linear. Why is, let us say, f of x equal to x square not linear? Okay. Simply because f of x plus y is x plus y squared, which is not equal to f of x plus f of y. This is one of the requirements for definitions of a linear space that is violated. So, this function is not non-linear, right. Again, we know this, but sometimes we suddenly get confused. So, I am just laying it out there. These are things that you have done pretty much since vectors and matrices were introduced, probably 9th or 10th grade. You have been doing this all the time. Most of the time you are not confused, but sometimes we do get confused. Is it linear or is it non-linear? Okay. And the linearity are those 7 or 8 rules that are there. 0 multiplied by something is 0, a plus a multiplied by x plus y is ax plus ay, f of x plus y is f of x plus f of y, f of alpha x is alpha multiplied by f of x, f of minus x is minus f of x, all of those things that you have learnt. F of x plus f of minus x is equal to f of 0, equal to 0, those things you have kind of learned that. Okay. So, f of 0 is another property of linearity. So, strictly speaking, x plus 1 is not exactly linear. Okay, surprise, surprise, it is not linear, it is called affine. Okay. So, again, I mean, these small things do cause confusion. Hurray, we talked about this linear, we have been considering this linear, affine, not very different, very similar, but still minor difference is there. Dx by dt, if you wanted to calculate for linear, straightforward. When it is affine, you need to do this, you need to take the x part onto the left hand side, multiply with e to the power minus alpha x on both sides and then integrate. Remember that integration from your 12th grade, 11th grade? That is the difference between linear and affine. So, coming back to what linearity means, the things that you have been doing, most of you may be okay, some of you might be a bit confused. That is because you are not thought explicitly about formal definitions. Okay. And one of the most important property that this leads you to is something that I talked about in last 2 minutes of yesterday's lecture, and that is principle of superposition, which basically just means f of alpha x plus beta y bar is alpha times f of x bar plus beta times f of y bar. And we did this in terms of the step response model in yesterday's class. Okay. You could do that because those were linear models. So, the linear combination, again we had covered this. This guy is a linear combination of p vectors, okay, where Ci's are all scalars. Okay. So, let us say x1 bar is, let us say x11, x21 and so on up to xn1, x2 bar is x12, x22 and so on up to xn2 and so on up to xp bar is x1p, x2p and p, okay. And y bar, which is represented as c1 x1 bar plus c2 x2 bar, is a linear combination, is obtained by a linear combination, okay, and this is also a vector, okay. And this we will represent this as x1 bar, x2 bar and so on up to, not xn, sorry, xp bar multiplied by c1 up to cp. Exactly what we did in the first slide of this lecture. We are just doing this, the exact same thing again. In the first slide we were given the equations and we represented in this way. Over here we are just doing the other way around, okay. So this is the representation, okay. And we talked about linearly independent vectors. So let us say you have vector 1 1 and vector 2 2. These are linearly dependent, okay. But on the other hand, if you had vector 2 1, that is linearly independent. What is the formal definition? If you have vectors x1 bar up to xp bar and alpha 1 x1 bar plus alpha 2 x2 bar, if this implies alpha 1 up to alpha p are all 0, then these vectors are linearly independent. If not, then they are linearly dependent. For example, if you have a vector 1 1 and 2 2, right. So you can write this as minus 2 multiplied by this plus this will give you 0 bar, right. So you have a case where your alphas are not all zeros, but still you can get a 0 bar. When can that happen? When the two vectors are not linearly independent, okay. If the number of vectors x1 to xp is greater than the size of those vectors, the dimension of the vectors, then those vectors cannot be linearly independent. So if x1 bar, x2 bar, x3 bar and so on are vectors in n dimensional space, vector space, then at most you can have n linearly independent vectors. Okay. Again, you know this is something in your first assignment I am asking you to prove. Okay. So with that we come to span of a vector, of vectors, okay. Span of vectors is a vector space which is formed by all possible linear combinations of that vector, of those vectors, okay. So what we mean by that is that, so we had talked about this, right, y bar equal to c1 x1 plus c2 x2 up to cp xp, okay. If we take c1 as 1, c2 as 2, c3 as 1.5 etc., that y is one specific vector. But if we let c1, c2, c3 vary arbitrarily, that becomes a family of vectors. For all possible values of c1 to cp, the entire family of vectors will form or constitute a vector space. That vector space is called span of those p vectors, okay. So let us look at a two dimensional space, and let us say we have this line or this vector 1 2. What is span? It is all possible linear combinations of that vector 1 2. So that is c1 and 2c1. for all C1, which basically means let us say C1 is half, then it is this value, C1 is 2, then it is this value, C1 is 0, then it is this value, C1 is minus 1, then it is this value, C1 is minus half, it is this value, C1 is minus 2, then it is this value, and so on. Okay. So, span of this guy is just a line that passes through the origin. What is span of 1, 2 and let us say 1 minus 1? 1 minus 1 should be here. The entire plane. Any vector in this entire plane can be represented as linear combination of these two vectors. Okay. So, span of 1, 2 and 1 minus 1 is entire R2 space, right. What if I ask you what is the span of 1, 2, 2, 4? It is that same line. Why? Because span of 1, 2, 2, 4 is going to be equal to C1 1 2 plus C2 2 4, okay, which is equal to C1 plus 2 C2, 2 C1 plus 4 C2, which is equal to C1 plus 2 C2 multiplied by and C1 plus 2 C2 multiplied by 2. Okay. So, this can be represented as C1 plus 2 C2 multiplied by 1 comma 2, and if we write this as alpha, then we see that this was that one line, right. Yes, no, confusing. This is an important property. So, if we want to go over again, we can. Okay. So, yeah, I mean that is what I covered in the previous slide itself. So, if this, then span okay, that is the definition of span. So, larger size problems, how to tackle them we will see. Smaller size problems, all you need to do is, let us say in the previous slide the examples that we took, multiply C1 x1 plus C2 x2 and see what all you can get with that particular multiplication. Okay. In your first assignment, you will have a question about trying to find out the span of a set of vectors and compare it by doing what is called as singular value decomposition. We will talk about singular value decomposition in tomorrow's class, if we have time, otherwise we will move it to next week. How many of you have not done SVD or you have not heard the term SVD? Can raise your hands. Okay, fair number. Okay, so we will talk about that. Okay, so then with linearly independent vectors, we have already defined them. Okay, if x1 to xp are linearly independent, then any vector y that is in their span can be represented uniquely as the linear combination. If these vectors are not linearly independent, then these A's are not unique. What that means is, if you have 1 1, sorry, the example was 1 2, okay. Let us say V trial was 1 minus 1. There is no way you can represent this as a linear combination of these two vectors. Why? Because if you have 1, 2, 2, 4, multiplied by, let us say, the solution vector S bar equal to Y bar trial, this does not have a solution. Remember, that is what we started off with. Okay. Let us say we say the Y bar 2 is minus 1 minus 2, right. This guy lies on that line. So, it can be represented as a linear combination of x1 bar and x2 bar. Okay. So, if you have 1, 2, 2, 4 multiplied by S bar equal to minus 1 minus 2, yes, the solution exists. Why? Because rank of 1, 2, 2, 4 is 1, rank of 1, 2 minus 1, 2, 4 minus 2 is also 1. That is what you have studied. We are just putting a different spin on it. What now we are saying is that this guy lies in span of x1 bar and x2 bar. Sorry, is an element of. This is not an element of span of x1 bar and x2 bar. Okay. So, how do you check whether Y is in span of x1 to xp? If rank of A matrix, which was found by making x1 through xp, and rank of A matrix that is formed by x1 to xp and Y, if those two ranks are the same, then Y is in the span, else Y is not in the span, right. Exact same thing that you have done before, just putting it in terms of vector spaces. And the final item is, if you have n linearly independent vectors in an n dimensional space, okay, then any vector in that n dimensional space can be represented as a linear combination of those n vectors. Okay. And we say that those n linearly independent vectors span the entire Rn space. And if there are n vectors that can span the Rn space, we can make those as basis vectors. For example, if you have vector 1, 2, 1 minus 1, they span the entire R2 space. What we mean by making them basis vectors is, instead of 0, 1, 0, 0, 1 to be your x and y axis, you can make the x and y axis as 2, 1 and 1 minus 1. So, you can change those axes to these axes. Okay. So, the natural basis, for example, is 1, 0, 0, 0, 1, 0, these are called natural bases. Okay. And any n linearly independent vectors can be used as basis for an n dimensional space. So, how do you do the change of basis? Okay. Let us say we have a vector y bar. Let us say we are representing this as y1, y2 up to yn. What that really means is that it is y1 e1 bar plus y2 e2 bar plus so on up to yn en bar, that is our y bar. Let us say y bar is represented in terms of y1 hat, y2 hat and so on up to yn hat in the space defined by Let us say this is how we define. What does that mean? That basically mean y bar is represented as y1 hat multiplied by v1 bar, y2 hat multiplied by v2 bar, and so on up to yn hat multiplied by vn bar. This is nothing but identity multiplied by y1 to yn. What is this? This is nothing but v1 bar, v2 bar up to vn bar multiplied by y1 hat, yn hat, right. But these two vectors are one and the same. Is the same vector represented in natural basis earlier and a new basis right now. So, we just equate them. So, we will find I multiplied by y1 to yn equal to v multiplied by y1 hat to yn hat. So, y1 hat to yn hat is nothing but V inverse multiplied by I, which is nothing but V inverse multiplied by this. Okay. So, this is old basis, this is new basis. Okay. So, just to summarize, so what we have done is defined vectors, vector spaces, talked about linear independence, linear dependence, talked about linear combinations, span, subspace, and talked about basis vectors. What we are going to then talk about is matrices and matrix subspace.